Let's start off today by actually looking at a practice problem of something that you would have seen in the homework that was due last night. So the question is this. I've got this reaction here. The magnesium is reacting with oxygen to make magnesium oxide. Delta H for that reaction is 1204 kilojoules. First question, is this an exothermic or endothermic process? So this answer comes down to sign. What does it mean when we have a negative energy? Which way is it going, in or out? It's going out. If energy exits, it's exothermic. So this is an exothermic process. Now, for the second question, we're asked to calculate the amount of heat transferred when 3.55 grams of magnesium react. And so for that question, this is where we would apply that stoichiometry-like approach. And so what we need to think about is that energy is on the same kind of comparison as moles in a conversion. So if I know that there are 3.55 grams of magnesium, my first step would be to convert the grams of magnesium into moles. And for that, I would just need the molar mass. 1 mole of magnesium is 24.31 grams. My grams cancel, I'm left with moles. And then the second step would be to convert the moles of magnesium into kilojoules. And this is where we need to think about this in terms of like a balanced chemical equation. The coefficient is related to the energy. So negative 1204 kilojoules for every 2 moles of magnesium. And so if I do that calculation, 3.55 times negative 1204, divide by 24.31, divide by 2, to 3 significant figures, I get negative 87.9 kilojoules. So the balanced chemical equation tells me how much energy is released based upon the stoichiometry of the reaction. I can use that to then tell me how much energy to expect when I have a set amount of reactant or when I make a set amount of product. And so this is where energy fits into that stoichiometry scheme. I can just do a simple mole conversion, and then once I'm in moles, I can use the stoichiometry of the balanced chemical equation to directly convert that moles into energy. All right, does that make sense to everybody? Were there any questions on that kind of stuff from your homework that you didn't quite get? Okay, so what we're moving into now then is we're getting into the look of, well, what else is there as far as calorimetry is concerned? We talked a lot on the first day about bomb calorimetry, about the idea that we could measure the internal energy of a system if it was kept at constant volume, and we could eliminate the work term using a bomb calorimeter. This kind of calorimetry is much more along the lines of the calorimetry that you did in lab earlier this week, and that what you're going to do in lab at the beginning of next week. You know, we used actual calorimeters instead of nested coffee cups, but the idea, the principle was the same. I had a closed system, which, yeah, you could make a technical argument that maybe it is a little bit open, depending upon how open those holes are and how much matter you think can be exchanged through those holes in the top and bottom, or rather in the top of the lid there. But for the most part, we could consider this to be a closed system. Chances are relatively unlikely that we're going to see a significant matter exchange taking place in a covered calorimeter. But the key attribute to this calorimeter is that it is at a constant pressure, because it is in a normal atmospheric condition. And so to that end, this becomes what we were discussing on Wednesday. This calorimeter and the calculation of Q that's associated with it helps us to determine the enthalpy of the system. But what we have to remember, the thing that is going to be the hardest part for us to put our brains around, is that what we are measuring inside of that calorimeter is not the system. In fact, it wasn't the system in a bomb calorimeter either. In both cases, we're measuring usually the temperature change in the water, and the water is not part of the system. Water is part of the surroundings. And so when it comes to this calculation, we recognize, okay, we're talking about M times C times delta T, that classic heat transfer calculation. But that MC delta T is of the water, is of the solution, is of the surroundings, not the system. And so this relationship here is super important. We have to understand that whatever we measure inside of that calorimeter is not the reaction itself. What the reaction is actually the opposite. So if the temperature inside of the calorimeter goes up, we know that that means it's increased in heat. That's an endothermic process to the calorimeter. That means that the system, the reaction itself, lost that heat, gave that heat away. That process is exothermic in terms of the system. And if the coffee cup, or if the calorimeter, if the water starts to get colder, and we notice a change in terms of the water being exothermic, well, that means that that energy went into the system, which means that the system got warmer. The system gained energy. It was endothermic. So the system versus surroundings piece is a really important one in calorimetry. Almost every time we're going to end up measuring the calorimetry, we're going to end up measuring the heat of the surroundings, not the system. So we have to remember to flip that sign when we start talking about the system itself. One other really important note. This equation will give us the value of Q, which we can turn into the value of Q of reaction. And that is related to delta H of the reaction. However, one really important note. Delta H values are usually measured on the molar scale. So just like what we saw in the previous example, where we had this based on the molar scale, 1,204 kilojoules for every 2 moles of magnesium, 1,204 kilojoules for every 1 mole of oxygen, 1,204 kilojoules for every 2 moles of magnesium oxide. That's the truth here as well. And so you saw this in the lab. To turn our Q values into delta H values, what did we have to do? We had to divide by the number of moles. And that's the case here as well. So if we're trying to evaluate the enthalpy of the reaction on a per molar basis, which is usually what we're trying to do, we usually have to do one extra step. We just have to do a division of the number of moles of reaction to get us there. Just kind of comparing the two here. The biggest difference between the two types of calorimeters is the conditions that we do, the way that we operate. Bomb calorimetry is done at constant volume. Coffee cup calorimetry is done at constant pressure. The process for solving the heat of the reaction is pretty similar. In the bomb calorimeter, we're not concerned with the mass because we're kind of measuring all of the calorimeter as part of the surroundings. And so that heat capacity takes into consideration all of that stuff. In coffee cups, we're using the more traditional MC delta T. Notice though that in both cases, we're using the negative sign for both of them. And why are we using the negative sign for both of them? Because again, the calorimeter is surroundings, not system. The other really important difference between them is what they give us as a result. In a bomb calorimeter, we end up getting a measurement of the internal energy change. In a coffee cup calorimeter, we end up getting enthalpy. Different things, different results. Calculations remarkably similar, but those nuances, those differences are enough to be noted, enough to be something we need to pay attention to. All right, let's do a quick review problem and see if we understood this overall concept. True or false? The system in a bomb calorimeter is the same as the system in a coffee cup calorimeter. All right, let's see how we did. Okay. Kind of split here. Kind of expected that. All right, the answer is actually false. Now, why is it false? Well, conditions. The coffee cup calorimeter is measured at constant pressure. The bomb calorimeter is measured at constant volume. That difference in condition speaks a lot to the system that we are measuring. So even if we did the same reaction in both calorimeters, the system would still not be the same because our fixed variables are not the same in each calorimeter. And so we would be measuring something differently in each one. So before we move on to Hess's Law, wanted to take an opportunity and work through a couple of example problems where we do some calculations related to Q. And so we're going to start with a kind of a simple one here. can we simply use the Q equation to figure out heat? And that's what this one is all about. So we are told that the specific heat of octane is 2.22 joules per gram Kelvin. Question is, how much heat is needed to raise the temperature of 80 grams of octane from 10 degrees to 25 degrees Celsius? Now, if Q is equal to MC delta T, this is a pretty straightforward application. My mass is 80.0 grams. My specific heat is 2.22 joules per gram Kelvin. My temperature change is final minus initial, so 25.0 degrees Celsius minus 10.0 degrees Celsius, which would give me a positive 15.0 degrees Celsius change in temperature. Now, before we proceed, just by show of hands here, looking at our units, looking at the calculation in front of us, is there a unit mismatch here? Raise your hand if you believe that there is a unit mismatch here. Okay. Yeah, the answer here is yes, there is a unit mismatch. But at the same time, the answer here is also no, because it really doesn't matter. And here's why. What we have to remember, the Celsius scale and the Kelvin scale are the same scale. The Celsius scale is just offset by 273 degrees. Now, we can prove this to ourselves. If I converted each of these into Kelvin, I would have 298 Kelvin and 283 Kelvin. And 298 minus 283 would give me the same 15 degrees Kelvin. Since we are taking the difference in temperatures, we can use Kelvin and Celsius interchangeably here. They're basically the same unit because they are the same scale. Now, if I had Fahrenheit and Celsius, I know that those two are not on the same scale. In addition to being skewed, there is a 1.81 to 1 ratio factor that you have to consider that the Fahrenheit scale follows compared to the Celsius. So you'd have to convert to get it to work. But in this kind of an application, if I see Kelvin, I can automatically turn that into degrees Celsius in my mind and be perfectly okay, and vice versa. Because ultimately the value is going to be the same. So if I'm calculating my heat, 80 times 2.22 times 15.0 to 3 significant figures, I get positive 2,660 joules. And that's all that we would have to do. For this problem, this is where we would stop. We don't have to go any further with it because all it asked us was how much heat was required. And we've figured that out. So for heat calculations, this is about as simple as they get. This is the kind of question that you could have easily been asked in the last homework assignment and gotten through with no difficulty whatsoever. Any questions about this before we move on? All right, then let's take a look at a slightly more complicated example. This is a classic calorimetry kind of question. In fact, it's so classic that basically this is the lab that you just did with a slight modification. Hydrochloric acid instead of sulfuric. So here's the scenario. I've got 0.2 liters of 0.2 molar hydrochloric acid. I've got 0.2 liters of 0.2 molar sodium hydroxide. I combine them together in a coffee cup calorimeter. The temperature goes from 22.15 degrees to 23.48 degrees. I'm given a specific heat capacity in terms of joules, milliliters, and Celsius. And it wants to know what the delta H value is. So a couple of things have to jump up to us here. First of all, we're being asked for a delta H of reaction value, which means that we're going to need either joules per mole or kilojoules per mole, depending upon how big this heat conversion actually is. Second thing that we need to notice is that our unit here is in terms of milliliters, not grams. And that's because we are dealing with solutions which are way easier to measure the volume of than to take their mass. So this is very similar to what you just did in lab. The only difference is that we have the same starting temperature for both solutions. So unlike the lab where you had to split off the acid solution and the base solution, calculate their delta T's separately, and then combine them together at the end, everything's at the same temperature. So I can combine everything together from jump. .2 liters is 200 milliliters. So Q of solution is equal to volume times specific heat capacity times delta T. 200 plus 200 is 400 milliliters. The specific heat capacity was 4.10 joules per milliliter degree Celsius. And our delta T, final temperature 23.48 degrees Celsius, initial temperature 22.15 degrees Celsius. Subtract those two from each other. We get positive 1.33 degrees Celsius. So to find the heat of the solution, we're going to multiply those three numbers together. 400 times 4.10 times 1.33 to three significant figures. I get positive 2,180 joules. So that is the amount of heat that went into the solution. Now we have to remember the cardinal rule of calorimetry. The solution is not what we're looking for. The solution is the surroundings. We're interested in the system. So we have to keep in mind that the heat of the reaction is the opposite of that heat of solution, which would be negative 2,180 joules. Now, if the question had asked for how much heat was transferred in this process, we'd stop right there. Negative 2,180 joules were transferred out of the system in this reaction. But it's not asking us for that. It's asking us for delta H, the heat of reaction. And for that, I got to go a little bit further. I got to take it a little bit further because we know that heats of reaction are either in joules per mole or kilojoules per mole. And right now I just have joules. I don't have the moles part. Where does the moles part come from? Well, it comes from a concept we saw in the last module. Molarity times the volume in liters will give me moles. So if I take my 0.200 liters times my 0.200 moles per liter, I'm going to get a total of 0.0400 moles. And that would apply to the hydrochloric acid. That would apply to the NaOH. That would apply to the NaCl. And that would apply to the water. Why in all of those cases? The ratio here is 1 to 1 to 1 to 1 to 1. So if I know the number of moles of any one of them, I would know the moles of everything, assuming that we started with equal amounts of reactant, which we did. And so in that case, equal amounts of reactant, there's no limiting reactant, no excesses to worry about. Everything that was reactants gets completely converted to product, which is, again, something you saw yesterday in lab. We did that very intentionally. So to find delta H for the reaction, I need to take my Q of reaction, divide by N, which would be negative 2,180 joules, divide by 0.0400 moles. And that would give me negative 54,500 joules per mole, which we could easily convert to negative 54.5 kilojoules per mole. Just remember, there are 1,000 joules in a kilojoule, so I can just move that decimal place 3 spots over to the left. All right, so there's your second kind of problem. This is kind of your classic reaction stoichiometry kind of problem. Or excuse me, reaction calorimetry. I put this solution in with this solution. They react with each other. Here's how the temperature changes. I can use those data to figure out the heat and to figure out delta H if necessary. Questions with this kind? All right, the last kind of calorimetry problem is also the most complicated. And I'll kind of frame it with this. If you can understand how to do this kind of problem, this is as complicated as of a problem as I can throw at you. So if you can understand this one, you're going to be fine for pretty much anything else I can throw your way. Here's the scenario. I've got a 20-gram sample of iron. I heat it up to 455 degrees in a Bunsen burner flame. I then take that glowing hot piece of iron, drop it into a beaker that has 100 grams of water in it, and the water is at 22 degrees Celsius. It comes to a thermal equilibrium. The final temperature is 27.9 degrees Celsius. Question is this: what is the specific heat for iron? Now, on the surface, this problem is really complicated. And it's not helped by the fact that it is kind of a complicated way of looking at things. But if we try to break it down into its pieces, what we will find is that this is actually a lot simpler than it seems. We know from our information that we could figure out the heat associated with the iron. We just need the mass of the iron, the specific heat of the iron, and the change of temperature for the iron. And with the exception of the specific heat, we know these 20.0 grams. We don't know C, but we know that delta T, 27.9 degrees Celsius minus 455 degrees Celsius. We know those things. Problem is, we don't know how much heat went into the iron or came out of the iron, and we don't know the specific heat. Similarly speaking, we can look at the water. The water would also be calculated in the same kind of way. The mass of the water, the specific heat of the water, the change in the water's temperature. And in this case, we do know all of those values. Mass of the water was 100 grams. The specific heat of water is 4.184. Joules per gram degrees Celsius. And delta T, we end at 27.9 degrees, and we started at 22.0 degrees. And so if I did this subtraction, I would have a positive 5.9 degrees Celsius. So from this standpoint, I can figure out how much heat the water exchanged. 100 times 4.184 times 5.9, rounded to two significant figures, positive 2,500 joules. The trick to this kind of problem is we have to recognize that the water heat and the iron heat are related. The question is how? How are they related? Okay. The water gained all of this energy. Where did it come from? The only place it could have come from, the iron. So here's your first law of thermodynamics right in your face. If this water gained a whole bunch of energy, it had to come from somewhere. Where did it come from? Must have come from the iron. So what's the relationship? Well, the heat of the iron must be opposite the heat of the water, which means that if this was positive 2,500 joules, this must be negative 2,500 joules. And now I can substitute because now I have values. The only thing that I'm missing now is the specific heat value. I also want to do the subtraction. So 27.9 minus 455 is negative 427 degrees Celsius. But to find the value of C, I need to divide both sides by the 20.0 grams and the negative 427 degrees Celsius. On this side of the ledger, they cancel. On this side, we have the basis for the problem that we're trying to solve. So what is negative 2,500 divided by 20.0 divided by negative 427 to two significant figures? It's 0.29 joules per gram degrees Celsius. So this kind of problem can be a little bit daunting because there's a lot of information being thrown at you all at the same time. What's important to understand, what's important to realize is that what we're talking about here are basically two separate processes. One process of heating and another process of cooling. And the thing is, the heating and the cooling are happening at the same time because they're in the same vessel, which means the energy that's being moved is the same. It's just in opposite directions. One is absorbing it, the other is giving it away. But it's the same quantity of energy in both cases. All right, any questions with this? All right, so a quick hypothetical here that'll kind of get us into Hess's law. If I was going to try to do this kind of chemical reaction, the reaction of solid carbon and gaseous hydrogen to make acetylene, how would I go about doing it? Can't really use calorimetry because neither of these are in solution, and neither would go into solution very easily either. Carbon as a solid, I have to worry about surface area. Hydrogen, I've got to keep it at some kind of a pressure. There's no real good way to measure this. And so the thought comes up, well, what if I didn't need to measure it? What if I could determine the delta H for that reaction without actually doing it? And yes, you can do that through something called Hess's Law. Hess's Law takes advantage of the fact that delta H is a state function. And as a state function, what that means is that it's path independent. So I can figure out delta H through a series of steps or by doing it directly. It doesn't matter. The value would be the same either way. So what we're going to leverage with Hess's Law is that when we have these situations where a delta H might be difficult to measure directly, either because it's dangerous or because it involves reagents that are going to be really hard to react together in their phases, we can take advantage of this state functionality and build together a mechanism of sorts, a series of chemical reactions that when I add them together, give me the reaction that I'm interested in. So here's an example of how that might be done. You can see here that I have three different chemical reactions. Each one of these reactions contains something that is present in the reaction that I'm interested in. The key that we're looking for, that we ultimately have to do, is we have to put these equations together in such a way that they actually match up. So in the case of the acetylene, a couple of problems with it. First of all, This equation has acetylene as a reactant. I need it as a product. It also has 2 acetylenes in it. I only need 1. The second reaction has carbon as a reactant, which is what I want. But I need 2 of them. This only gives me 1. This third one, perfect. I need hydrogen as a reactant. It gives me hydrogen as a reactant. I need 1 hydrogen. It has 1 hydrogen. So, ran a little bit short on time. I'm not going to be able to walk through this example fully. So, what I'm going to do instead, there are a couple of practice problems I have that I want to walk you through. I'm going to walk you through them in a separate supplemental video that I'll publish over the weekend. And so if you're worried about kind of, picking your way through that Hess's Law problem, those problems that are in assignment 6-3, look for that video to come out. It'll help a lot. Since we are out of time for today, make sure that you hit this quickly on your way out for the day. And then, again, primary focus this weekend. Start to get ready for that review session. Start to get ready for the exam on Wednesday. During class on Monday. All right. Have a good weekend.